we are basically done with basic consumer theory, which is very impressive. And that means we can now start studying producer theory. If you remember, we started out with a supply-demand diagram, and we looked at that and talked about where those two curves come from, the supply curve and the demand curve. And we decided that we didn't really know, and then we delved into consumer theory, and now we understand where that curve comes from, the demand curve. And that's, of course, for one consumer. So remember, we derived the demand curve for one consumer. For a whole market, it's actually not too difficult to get the demand curve from all the consumer demand curves. What do you think you need to do? So we have the consumer demand curves. To get the market demand curve, we need to add them up. Exactly. So, so we know that. Okay, where does the supply curve come from?
Adding up all of the suppliers.
Yes, adding up all. Okay, adding up all the individual supply curves for the firms. So where do individual supply curves come from? Costs. All right. So we need to somehow model costs, right? And at first, you know, that might seem kind of simple. Like, what would be, you know, if I wanted to create an Excel spreadsheet, what would be the cost of that? If I wanted to pay, let's say, a few students to create some fancy Excel spreadsheets for my class, what would be the cost of that? Not in dollars, but, you know, in principle.
Opportunity costs.
So how would I know what the cost would be?
Time that I get.
Yeah, it would be time. Yeah, you're saying the same thing, I understand, by saying opportunity cost. So it would be time. Okay, so I would have to pay you for your time. How much time would I have to pay for? How much time would it take you to develop a fancy spreadsheet for microtheory? Like an hour? 2? Okay, you must be good. Would it take 2 hours for everyone? No. So my point is, you know, when we say cost, that's a little more ambiguous than you might want to think. Because how much it costs for me to pay you to develop an Excel spreadsheet depends on whom I hire, right? So cost might be different for every one of you. If I have this big tree in my backyard and I want it cut down, how much does it cost me?
Different depending on the supplier.
It depends, right? So there are several ways to cut down a tree. What would be one way? Buy an axe, exactly, and just hack at it, and eventually it's coming down, right? What would be another way?
Burn it down.
Burn it.
That's funny. Burn it down. I'm not hiring you. We've established that. So, what would be another way? Chainsaw. You could get a chainsaw and cut it down with a chainsaw, right? So, between those two ways, if you had to guess, you know, having a tree cut down here in Appleton, Wisconsin, or having a tree cut down in my home country in Hungary, where do you think it will be more likely that it'll be cut down with a chainsaw? Here. Why is that? Yeah.
Labor is expensive.
Yeah, exactly. Labor is expensive. So labor is an input into this production process. Labor is expensive, so you expect a different kind of production process. What we're getting at here is that this whole question of costs is a little more complicated than you might think at first. And it has to do with technology. It has to do with production technology. When you make the Excel spreadsheet, that, you know, we all have different production technologies. When you cut down a tree, we may have different production technologies. We may use different levels of capital, right? Chainsaw versus an axe. So that's exactly what we want to get at today. That's what we want to model today. And this all comes down to how we model the firm in economics. The firm is basically the producer. So in my little picture here, I'm showing you our model of the firm. And it's really, really complicated. Here's how it works. Okay, so listen carefully. The model of the firm involves these things here, which we call inputs. Very, very technical term. So these are called inputs, okay? And then at the other end, there is this thing which we call the output. So this is our model of the firm. You got it? Right? You understand? The inputs go in and the output comes out. That's our model of the firm. So if that sounds kind of ridiculous, it sort of is kind of ridiculous. But you know, think of it this way. It's very simple, and we still get some mileage out of it. So this is going to be basic economic theory, and we have to start basic. I don't want to pretend that in economics, you know, we don't have any more deeper understanding of firms than this, because we do. And in fact, you can take a whole course on the economics of the firm here at Lawrence. But our basic model of the firm is just this. Sometimes we call it the black box model of the firm, because it's like a black box. We are not going to ask at all what's in here. We won't even think about it. You know, inputs go in and the output comes out. And that's all. We're not going to ask any questions about this thing here. If you think about it, our model of the consumer is a little bit similar in that we don't actually even ask what happens in people's heads or how they come to the preferences that they have. We just say they have certain preferences. And where that comes from, we don't really ask in basic economic theory. We have some more sophisticated models where we do. But in basic theory, we don't even ask that. So it's kind of the same with these firms. We don't even ask what happens in here, even though, you know, even though it seems like that would be pretty valid territory for economic science, right? And actually, there is a lot of work on what happens in here. But for our basic theory, this is going to be really simple. We just say there are these inputs that go in, and the outputs that come out, and all we need to do to model the firm is describe how that happens. And we can describe it using the production function. So, for example, the inputs might be capital and labor, and very often that's how we'll talk about inputs, because those are very common inputs. So if you think about some kind of basic manufacturing process, well, you need labor, obviously. Not obviously, I guess, but you probably need labor, and you probably need machines and land, and we call that capital. And that goes in. Those are inputs. Usually we denote them by K and L. And then we have a function, f of K and L, and that tells us for any given combination of inputs K and L, the output level Q, which stands for quantity. So that's basically how we can describe what a firm does. And we call this technology. So this describes the technology of the firm. You know, it tells us what combination of inputs the firm can use to produce a certain output. If you run a company that cuts down trees, you might have chainsaws, and you might have axes, and you might have access to labor. So you could decide to cut down 10 trees using a lot of labor and no chainsaws, or you could decide to cut down 10 trees with just maybe one person working at it using a really, really good chainsaw. And the quantity level would be the same, but you would be using different inputs. So that's how we describe production processes. So here are the questions then for us today. The firm that is characterized by this technology, the production function, decides to do the following things. So these are the decision variables for the firm, right? And I'm asking for your help here. How much fill in the blank to produce? Yeah.
Product?
Exactly. So you could say product or output. How much output to produce? And the second question is, how much of each input you use? And this is not the order in which you might ask the question, those two questions, maybe. But these are basically the questions you need to decide. These are the decision problems for the firm. The firm's goal, of course, is to, yes, maximize what? Profits. So we know that. You probably all knew that from intro even. Yes?
So how would we define labor? Is it like all the inputs or the money spent on the inputs?
So how would you define labor
Capital, sorry.
or capital?
Yeah.
Okay. I think what you're asking is how you measure capital,
Yeah.
right? And maybe you would, maybe you would measure it in money, but I would rather think of this. I think it will be a little easier if we think of this as, let's say, machine hours. So for a simple example, think of you have a certain machine, and maybe it's a chainsaw, and we measure how many hours you use that. That's an input into the production process. And for labor, you could do the same. You could measure it in hours worked, right? So it doesn't have to be in people or something. It can be simply hours worked, and there might be different kinds of labor too. That's what we established right away when we talked about the Excel spreadsheet. So, of course, this is a very simple model. And when we talk about just two inputs, that's really, really simplistic, right? And you realize, of course, in a more sophisticated model, you might have lots of inputs, and the production function would be more complicated. But here's basically what we need to do to understand the theory of the firm for basic economic theory. We just need to figure out how to model these questions. Profit, let's start with the last one, profit maximization. How do you maximize profit? Well, first of all, what is profit? You all know this, right? So what's profit? Yeah, Umar.
Revenue minus cost.
It's revenue minus cost, so that should be, pretty simple. If you actually wanted to put a formula to it, what would it be? Yeah, Brianna?
Output minus in.
Let's start with the revenue. What's revenue?
The money that you make.
The money that you get, and that would be how would we calculate it then?
Times quantity
It-
supplied.
Yeah, it would be price times quantity. So I'm going to write it here. That's revenue, right? Price meaning price of your output times quantity that you produce and presumably sell. So what are we choosing then to maximize profit? What variable is this firm choosing? What's the decision variable for this firm when it's maximizing profit?
Quantity.
It's quantity, how much to produce, right? So the firm chooses quantity to maximize profit. That's a function depending on quantity. And the function says revenue minus cost. And the revenue part is P times Q, and the cost part is what?
Capital plus labor?
It's whatever, exactly. So whatever your total cost is, whatever you're spending on. Maybe you're spending on capital, and maybe you're spending on labor, and maybe other things. I'm going to cheat a little bit and just say it's your total cost. So TC is for total cost. Okay, so total revenue minus total cost, that's the profit function. It depends on quantity. You maximize it by choosing quantity. Are there any constraints? Yeah.
So price minus margin.
Quantity by too much, you have more cost eventually.
Okay, so when you say if you increase quantity too much, you'll have higher cost eventually, what you're saying is you want to maximize profit. We already got that. So we have that. You're maximizing profit as a function of quantity. But what I'm asking is, in this maximization problem, because by now this will come down to actually writing down a maximization problem and solving it, right? So in this maximization problem, are there any constraints? Yeah, Austin. What is that? That's a good practical point about inventory. So yeah, you might have constraints like that, like how much inventory do you have of a certain input. That would be a very practical point, which we are not even going to worry about here. So this is really high level. Yeah, only.
Profit can be negative. You can't have a negative profit because otherwise you're from.
Well, first of all, so you say profit can't be negative. First of all, we'll see about that. Who knows? Okay. But again, you're just saying you want to maximize profit, right? So we've got that. Theo?
It
seems like there's no real constraints on it, because you could have like a really high profit or a fairly large negative profit, but if our profit gets too large in the negative direction, legally we might not be able to continue operating because of the hits or something like that. But I don't know if there's actually any constraint on a function for optimizing.
Yeah, so you're not sure. It's okay, Bjorn, what do you think?
The demand function.
Okay, so you want to say how much you can sell is your constraint,
Yeah.
which is a good way to think about it as an economist. You know, you're giving good answers. These are good answers. They are not the answers to this question, but they are very good answers. You know, that's true. You might be, as a firm, when you're maximizing profit, you might be constrained by how much you can sell in a sort of colloquial sense of the word constraint. So for this maximization problem, the reason you're confused, I think, is that the constraint is built into that equation. I cheated. I built it right into that equation. Do you know how?
Yeah, because I think it should be capital, like how much capital you have in your firm to spend on stuff.
You're saying how much capital you have, which is almost like Austin's point about inventory, right? A little bit. But my point is, it's close. My point is, you're constrained by whatever technology you have. That's actually a constraint.
Price.
You can only produce a certain quantity given the technology you have, and you're actually constrained by that, right? So by simply talking about total cost, I hit that.
It should be quantity time average cost.
Well, no, it's not it's not that we are talking about total cost and not average cost. It's that by talking about the total cost function, I hid the fact that you need to think about what combination of inputs you're using, actually. And so, because what goes in here is, let's say, capital and labor, all right, or whatever inputs you use, right? So it might be capital and labor, and I hid the fact that you can only use certain combinations of capital and labor to produce certain levels of output, because you're constrained by whatever technology you have. So your real constraint is the technology you have. And theory, you're right. Maybe when we maximize this profit function, technically there might not be any constraints, actually, because by the time we get here, we have already essentially dealt with the constraints by coming up with this total cost function. Okay, so we'll see how this works. Let me just point something else out. Something else that I think I may have managed to get past you here. So we say the firm chooses quantity. And that's the main, that's how it maximizes profit. Now let's think about real life. What does the firm choose? If you think about real firms.
Price.
So you might, first of all, maybe they choose price as well, which is a good point. And then we'll have to start thinking about demand. And yeah, we'll get there. Maybe they choose price as well, but even not thinking about price, maybe they have, so do they have market power? That's the question. If they do, maybe they have some, maybe they can choose price. If they don't, then they don't choose price in any way.
You would choose the maximize about profit. Profits.
Well, think about real life firms. What do they choose? Yeah.
They choose what to make.
Yeah, exactly. They choose what to make. Do you understand? If you think about a real life firm that makes these tables, you know, it's not that they, in their big boardroom, big beautiful oak table, right? They don't sit down and go, okay, how many? That's not how it goes. They think about, how do we come up with these fancy modular tables that can be used, right, the way you're using them. So what they really, and this is more important, because if you produce corn and you can only produce one kind of corn, maybe then you're deciding how much, right? That's the big question. But otherwise, for most firms, what they are really deciding is what to produce. And they don't just produce one thing, they produce many things. And they need to, and they are constantly coming up with new things to produce, right? So the real issue here that I sort of hid just by setting it up this way is that real firms produce various things, a variety of things, and new things all the time. And the really important decision is what they produce, and not just how much. So we are really, really simplifying things here. But we are doing it for a reason. We want the simplest possible model. Okay, so here's where it starts. And you can get more fancy later on, but here's the simplest possible model. The firm decides what inputs to use to produce a certain quantity of output, and that's it. Okay, so how does this go? I'm taking this a little slowly because eventually we are going to get into the math and derive all these things. But I want you to understand where we come from, and I'm doing this a little differently than the textbook is doing it. The textbook gets right into, here are the cost functions, and here's the production function, and I would like you to understand why we set up the model the way we do, and I would like you to understand conceptually how this works, and to actually be able to go from the firm's technology, which is really what's given. That's what we know about a firm. That's what defines a firm in this basic theory. I want you to be able to go from that to the cost function to profit maximization. And the textbook doesn't really ask you to do that. So I'm getting at this from a somewhat different angle and maybe looking at it just a little more deeply than the book does. But hopefully you realize that it's about the same thing. The chapters 5 and 6 are about the same thing as what we are talking about right now. Okay. So the firm's technology is described by this production function, and that's what's given about the firm. That's what we know about the firm. And we go from there to the cost function, the cost of producing various quantities. So we go from here to the cost function, and that's not obvious. So we'll need to figure out how to do that. Once we have that, we can go from there to the profit function. And now we are in a position to actually write down that maximization problem and get to profit maximizing choices. What do you think will influence those profit maximizing choices? So what exogenous factors might influence that quantity that you produce, and also how you produce it? What exogenous factors might be really important? Yeah?
Cost of labor or human capital?
Exactly. So cost of labor might be very important. So when we talk about what factors influence this, we need to go back right to the beginning and say, yeah, the cost of labor. Sometimes we call that wages, right? The cost of capital, similarly, very important. And this goes back to the chainsaw versus axe example, right? And then what else might, these are both prices, by the way. You realize that these are just prices in the marketplace, the price of labor, the price of capital. Yeah, Jimmy?
The price of the good you're using?
Exactly, the price of your output. So we usually just use P to denote price, but the price of your output will be very important too. So these are all exogenous factors that are given that somehow need to find their way into this whole derivation, because they will be important. Yeah.
Are we thinking about like the government like setting limits, price floors, or price ceilings in this equation?
We are not even thinking about price floors and price ceilings and regulations yet.
Okay.
This is really, really just very basic so far. Yeah. Okay, so let's try to do this. I'm going to give you an example, and I'd like you to try to work through this, and then we'll see if that gives us the idea of how to do it more generally. Let's just say that we are producing apps, and there are two inputs into this production process. So we have a firm. The firm produces apps. It uses labor. We'll denote that by L, and it uses software that's developer software that you can use to make apps. And you can use various, we'll just say you can use various quantities of that input, the software. There might be different kinds of software. There might be better ones and worse ones, and we might want to somehow adjust for quality in how we measure that input, that software. We won't worry about that in detail. We'll just say, you understand what I'm saying. We can say, if you use more fancy or more software that's better, you probably need to use less labor or less qualified labor. So there's a trade-off there. And the output is apps, quantity of apps that you produce. You could, for output, you could decide to measure it in lines of code. I don't know what would be the right way to measure it. You can measure it in number of apps that you produce. In some way, we measure the number of apps you produce, or the quantity of apps that you produce. And this production function shows us how there is a trade-off between using more labor and less software, or more software, less labor. So the output, Q, is given by this production function, square root of L times square root of S. For any inputs L and S, you know how much output, how many apps you can produce. All right, so I'm going to tell you that the price, we don't know what prices are yet, although I'll tell you in a minute, but price of the output will be denoted by P. Price of labor is W, wages, and price of software is going to be C sub S. And my question is, how much does it cost to produce some given quantity Q? That's how we need to understand going from technology to cost function. So let's start with a really specific example. We want to produce 10 units of output. And wages are set at 2, cost of software is 8. Okay, so I'm telling you very specifically, you know the production function, you know the relevant prices. You don't need to know the price of the output, by the way, because I'm not asking you to maximize profits yet. I'm just asking you about costs. I'm asking you how much would it cost to produce 10 units given these input prices. Okay, I'll give you a few minutes. So actually come up with the answer, okay? I mean, if you want to talk to each other, come up with the answer. Actually figure out how much it would cost.
It literally just be 2 times US. Every year 2 times UK. Because you have the cost of labor is wages and the cost of software is S.
I think you need a quantity of labor and software.
Well, for wages too.
It's a
Labor,
price.
the cost of labor.
Oh,
the cost of
you
wages
just said
too.
it.
And the
Cost of them 2 times 10, you're 20, and you're 80.
Cost of labor isn't just two, it's 2
Okay, what do you have? Let's go around. Does anyone have any candidate answers? I know you're working on it. Yes.
20 hours of labor and 5 software.
20 hours of labor and 5 software, and how much is it costing you?
$80.
80? Okay, so there's a challenge. Can anyone do better than 80? Anyone? Can you see how this kind of thinking is actually helpful in a real world situation? Like, can you understand how this might be a question you would want to ask in an actual firm? You know, you could easily have a situation where, all right, so there might be different products, but once you think about a product, there actually are many ways to produce it, and how do you find the least cost way of producing it? Well, this actually is sort of how. So what you're doing now could be pretty relevant in a real world situation too. Did you get an answer?
I don't think it's right.
No. Okay. No, you didn't. But you were doing something interesting, though. I mean, you started with an equation that said 100 equals L times S. Why did you start with that?
I mean, you know that Q equals 10, so we just put 10 in the equation, which is square root of L times square root of S equals to 10. So
Yeah.
we can know it just
Okay.
put square in the both sides of the equation, so we can get L.
So you know that the production technology allows you to produce Q units of output with square root of L times S inputs. And you just wrote that down, and that actually allows you to write one input in terms of the other input. Because you know you want to produce 100 units of output. Yeah, exactly. Okay, so that's actually start. And here's what it looks like. Remember, we did this with the consumers problem too. We thought about it intuitively. We solved it graphically using indifference curves and the budget line, and then we derived it algebraically. So we can do the same thing with producer theory as well. All right, so what do we have on the axis? we have labor and software. These are the two inputs. So here you have every possible combination of inputs. And what we need to show here is the technology that's available to the firm. So we need to somehow show the production function. Remember, the production function was F, function of, in this case, labor and software. What do you think these lines are that I'm showing? How would you describe one of these lines? What would be a useful way to represent graphically that production function? Yeah.
Production function at each given quantity.
So what would be common between all these combinations of labor and software?
Cost.
Not the cost. No, what would be the same? Quantity, yeah. So this would be called an isoquant. Because along this line, quantity produced would be constant. So this might be the one where, let's say, Q equals 15. I'm just making that up, okay? So this is not to scale or anything, but this is another one. Maybe here Q equals 12, and maybe here Q equals 10, right? Each one of these corresponds to a different level of quantity, because we already figured out that you can produce a given quantity using a number of different combinations of inputs. So we could describe the production function, the technology, by showing these isoquants. The isoquants are the lines along which quantity is constant. Okay? By the way, if you think about it, the relationship between the production function and these isoquants is exactly the same as the relationship between indifference curves and the utility function. These isoquants are level curves of the production function. Okay, so you can think about that. So that's half of it. Okay, we've got the production function on here on this graph. What don't we have yet? Cost. Okay, so we don't have cost. So we don't have cost on here yet in any way. How can we get at costs? Well, look, I'm using the same axis exactly. Okay, so we have software, labor, different combinations of software and labor. What do you think I'm showing? What is common among, for all these points on this line? What do you think? Yeah.
The cost decreases with increase with labor.
No. What is common? What do these points have in common along this line? What do you think? What would be? Yeah, the cost. Exactly. That would be useful. If I showed, these are the points that have the same cost, that would be useful. And for that reason, we would call this an iso-cost line. And it corresponds to a certain level of cost. It intersects the software axis at 6. If you assumed that input prices are like in our example, 2 for wages, 8 for software, then what cost does this line correspond to? What is the cost along this particular line? $48. $48, because this point is on it. This point is, I'm using 0 units of labor or software. Software costs 8. I'm using 6. Therefore, total cost would be 48. And along that line, cost is constant. So this is the line that corresponds to cost equals 48. This is the line that corresponds to cost equals what? 4 times 8, which is 32. This is the line where cost is equal to, that's about 2.5 times 8, 20. Yeah? You see how this goes, right? So we have these ISO cost lines that tell us for any particular cost, what are the combinations of inputs that cost that much? Okay, how do we get the optimal way to produce a certain level of output now? Somehow we need to put these two together, right? So somehow we need to say, if I choose a particular level of output, like Q equals 12, or Q equals 10, which cost line is it going to be on? There are many ways to produce 10 units of output, right here, many, many ways. I need to pick one. How am I going to pick the one that has the lowest cost? Can you see how there could be many cost lines that intersect this isoquant right here? There could be many cost lines. Which one am I looking for? I'm looking for the lowest possible one. I'm looking for the cost line that's going to somehow be the lowest possible cost line, but still intersect that indifference curve, which means it has to be tangent to it, right? Which means for Q equals 10, this is it, right there. That's the combination. That's going to be the combination of labor and software that gets me the lowest possible cost. Yeah. That's a good question. What is the slope of the cost? No, let's not say cost function. Let's say iso cost line. What is the slope for the iso cost line? Yeah, it's rise over run, so it's going to be negative CS over W. You're guessing. Could we measure it? I mean, look, you could just pick one and do rise over run, right? Yeah? So what is it going to be?
Oh, it should be W over CS negative.
It should be negative W over CS. Yeah, exactly. You should check that. You should see if you understand that. Of course, you can check what it is, as a number. Like, pick this one right here. This intercept is 2. This intercept is 8. We have negative 2 over 8, negative 1/4. We know the input cost, so yeah, you can see it's going to be negative W over CS. But think about that. So what happens here, we basically using isoquants and isocost the graphical solution, but since you got there pretty quickly, let's go to the algebraic solution first, and then we'll talk about the graphical way of solving this too. Okay, so indeed, you can do that, right? You can write down, we know that we want 100 units of output, and therefore, just as you said, Shuwei, we can write L equals 100 over S. And you know what's interesting? That's basically a constraint, right? That's a constraint. But what are you trying to do? And this is what you're doing next. I think you went wrong somewhere, but what you're trying to do is minimize your costs. So you're minimizing your costs subject to the constraint that you want to produce 100 units of output. Okay, so what we want is minimize. Let's write down what the costs are. Well, the costs are 2 times L, wages times L, cost of capital times S, cost of software times S. So we want to minimize this function. We can actually, once we know that L equals 100 over S, we can actually plug that in there, right? And minimize 2 times 100 over S plus 8 times S. And we can write it, then we can write that out. So minimize 200 over S plus 8 times S. And what you need to do then is take the derivative and set it equal to 0. So how do you minimize a function? Right? If you let's assume that we get lucky here, and the function you have actually looks sort of like that. So it actually has a minimum. We should worry about that. But for now, let's just hope that it's okay. You're looking for that point. That point is where the derivative is equal to 0, right? So we take the derivative, and the derivative is minus 200 over S squared plus 8. And that should be 0. And if you solve that, you get S squared equals 25 and S equals 5, L equals 20. Is that how you got it, Christian? Okay, it worked, right, this time. But this is how you can get it every time. So we actually got, and you can plug that into now the cost function to get the cost, which is in fact 80. Okay, so we actually got this. For 100 units of output. We can now ask some pretty interesting questions, right, which we couldn't really ask before. Actually, let me ask you the question and see if you can get this right. What would happen to this cost of producing 10 units of output if wages doubled? So your cost of producing 10 units of output is 80. By the way, we can see that you're spending 40 on wages. You're spending 40 on software, right? You can see that too. You get to 80. My question is, what happens to this cost of producing 10 units of output if wages double? You could see how this could be a pretty realistic question too, right? So you're sitting around and you're producing something in Seattle and you're asking yourself, we are paying minimum wage. What happens if the minimum wage is raised to $15? What's going to happen to our costs, right? I'm asking you that question. What do you think?
Well, I was just going to say that like labor might decrease and software, like the use of software would increase because it's just costing too much to have that amount of labor still.
So we shouldn't just take the amount you spend on labor, which is 2 times 20, and multiply it by 2 and say, looks like we would be spending, if wages were 4 instead of 2, looks like we'd be spending 80 on labor, not 40, and therefore our cost would go up to 120. We shouldn't just do that.
I mean, I think that would be correct, but that's not the cheapest way.
So what you're saying is it wouldn't be correct.
Yeah, it would not be correct.
Yeah. Yeah, and it wouldn't be the cheapest way because, Bjorn, what were you going to say?
I think it would be like 113.
Maybe 113?
Yeah.
How much exactly?
0.137.
Maybe I haven't actually checked. But if you wanted to actually answer but you're right, Harry, your first instinct was exactly right. I mean, I think if you don't really understand the economics behind this, I think your first answer might be what I said. Well, we are spending 40 on wages. If wages doubled, we'd be spending 80. So, you know, our cost would go up to 120 for 10 units. That might be your first answer. But if you understand that you're minimizing costs and you're actually optimizing, reacting to exogenous variables, which include the prices of inputs, then you know that that's not true. Now, how do you get the right answer? To get the right answer, it would be very helpful to have maybe a formula for your total cost that actually depends on input prices and actually depends on the quantity you want to produce, and you could just plug in those things. If we just plug in those things, we could tell for any particular input prices how much costs would change if they changed. Okay, so can we do that? How would we do that? Give me the strategy. What's our strategy? Yeah, Mohammed, what's our strategy?
Maybe don't put numerical values and solve it as a variable.
Exactly. Don't do the same thing we just did. Do the same thing again, exactly the same thing. Except right here, don't put 2, just put W. And here, don't put 8, just put C sub S. And here, don't put 10, just put Q, right? And solve. And we should be able to do that, right? Okay, so here it is. I set it up for you. Why don't you do it? At the end, what will you have? It is going to say, what are you looking for? You're looking for, your answer will be, not exactly, but you know, what are you looking for? Your answer will be the total cost function. It's going to be a function of total cost as a function of input prices and quantity produced. Let's go through this together, okay? I see that some of you have the answer. If you have the answer, by the way, you could tell me right now if, for the previous example, if the total cost was 80 to produce 10 units of output, by what percentage would that go up if we doubled wages? What is that?
Square root of 2.
It would go up by a factor of square root of 2. So about what percentage? What's the square root of 2? Does anyone know that?
4.
Square root of 2 is about 1.4, so maybe 40%? Okay, roughly speaking. So we could answer that question really easily once we have the answer here. Okay, so let's do this. First step, what do I do?
get labor or
Get labor or software
in terms of other terms?
in terms of the other variables. So we know that Q equals square root of L times S. So from that we know Q squared equals L times S. And from that we know L equals Q squared divided by S. Okay. That's good. So that's done. And now we rewrite the cost function, knowing that we plug this into the cost function. So we have wages, yeah, exactly, W times Q squared divided by S plus, exactly. And we are minimizing that. What are we choosing?
The derivative equals 2.
We are choosing what variable? S. It's not a bad idea to write that down, because we also have CS in here and we have Q in here, and you could easily go wrong, right? If you forgot what you're trying to do, you're choosing the input variables. So you're minimizing that. So we want to take the derivative with respect to S. Everything else is a constant, and set that equal to 0. So what's the derivative with respect to S? We have S to the minus 1. So we get a negative sign, and then W Q squared over S squared, exactly, plus CS. And that should equal 0.
So S should be equal to Q times square root W over CS.
So from that you can solve for S. And if you solve for S, you get Q times square root of CS over W, right? Or W over CS. You're right, yeah. W over CS. And this last step was just solving for S. Okay. So that's one input. What's the other input? The other input is L. But we already have a formula for that, right? So we can use this and this to say L should equal, we just basically plug in what we got for S. We plug that in here, and we get L equals Q times square root of CS over W. Okay, so that's almost our solution, because we don't have the cost function quite yet. To get the cost function, what do we need? You just need, yeah. How did I get L? So we already expressed L in terms of S. That was just from this equation. After we solved for S in terms of Q and W and CS, we took that and simply plugged it in here. And now we can, and now just simplifying, now we get this. So I'm skipping the steps of simplifying, and I'm doing that knowing that you will go through this in painstaking detail after class.
Why
right?
is it CS over W and not the other way around, W over CS?
If you, again, if you plug in this in here and simplify, it's going to be CS over W. The reason is that this W over CS will end up in the denominator, and so it will flip to CS over W. Yeah. Yes?
I mean, it's pretty tricky. I think if we just keep going, and we can get about the TC, I mean about the total cost, right? I mean,
Yeah. So that's what we are about to get the total cost.
Yeah, I mean, just use W and CS to get the total cost, and it just doesn't make sense.
Well, let's see what it is, okay, first. So what is total cost then? Well, it's going to depend on quantity, it's going to depend on wages, it's going to depend on the cost of software. And the formula is up here, is W times L plus CS times S. But we know now what the optimal choices of L and S are. We solved for those, they are right here. That's the optimal choice for S, and that's the optimal choice for L, the cost minimizing choice. So we plug those in. So instead of L, we write W times whatever we got for L, and we got Q times square root of CS over W. And then we write CS times S, but instead of S, we write what we got for S, which is Q times square root of W over CS. Okay, we can simplify that, right? So now if we elaborate on that a little bit, and let's take this, you know, a little slowly. So you have a W here, and you have a square root of W in the denominator. So because W equals square root of W times square root of W, one of those cancels out with the square root of W in the denominator, and you just get a square root of W and a Q and the square root of CS. Plus, you have a CS, but then in the denominator you have a square root of CS. You get overall square root of CS times Q times square root of W, which is of course just 2 times Q times square root of W times CS. That right there is total cost. So that's the cost function, right? You plug in any input costs, W and CS, and you can tell what the cost function is. So that's how we can tell if I double the costs of wages, if I doubled wages, the cost of labor, if I doubled wages, I would increase total cost by a factor of square root of 2. That's how I know, okay? So now we derived, from the technology, we derived the cost function. And you could take this and maximize profit. So now you could say, okay, let's maximize profit by writing down, let's say, in this case, you could say, so what's total profit? Profit as a function of Q, and I'm not going to show that it's a function of wages and the cost of software here, but it would be output price times Q minus 2 times Q times square root of WCS. That would be your profit function. And now we could maximize that by choosing Q. And when we do that, we are implicitly always choosing the cost minimizing way of producing any given quantity, because we already derived this cost function that does that. It's built into it. Minimizing cost is built into this cost function. Okay, so the last thing I want to show you is the same thing graphically, to quickly represent exactly the same thing that we solved for algebraically. So to quickly summarize here, we went from describing a firm by its technology to deriving its cost function from its technology to choosing quantity of output using the cost minimizing cost function. Graphically, here's how we did it. We didn't actually we haven't graphed the cost function yet, but you'll read about it in the book, and we'll do it also tomorrow and Thursday. Algebraically, we went from the production function to the cost function to the profit function. All right, so think about this, work through it again, and we'll get some practice doing this tomorrow and Thursday.